Hello students, welcome to EPG Pathshala. I am Tanushree Shahadas Gupta, Professor and Associate Dean in S.N. Bose National Center for Basic Sciences in Kolkata. I belong to the Department of Condensed Matter Physics and Material Science. I am also the coordinator of the thematic unit of excellence on computational material science set up within S.N. Bose Center. In this lecture, we'll talk about the single-electron approximation to the many-electron problem. In particular, we'll talk about the Hartree theory. As we all know, the matter consists of atoms. Within the atom, we have nucleus and electrons. The problem of understanding a material, therefore, boils down to solving a problem of a collection of mobile nuclei and electrons which are interacting via electrostatic force. Understandably, this is an impossible task to solve given the large number of variables. Approximations are thus inevitable. Based on their masses, one can decouple the motion of electrons and nuclei, which leaves us with an electronic Hamiltonian, where the quantum mechanical kinetic energy of the electrons and the Coulomb interaction between nuclei and electrons and that between nuclei and electron, they are in balance. Solution of this problem provides us with the knowledge of electronic structure of the materials, which plays a crucial role in deciding many of the properties of materials, namely the electronic, the magnetic, the optical properties, and etc. Electronic structure thus plays the central role in understanding materials, which can be both inorganic as well as organic. This understanding leads to the optimization of known materials with an ambitious goal of designing new materials. No wonder that the study of electronic structure forms an important topic in the modern-day computational material science. This has become especially important with the advent of present-day high-performance computers. Following Moore's law, the processor speeds or the overall processing power for computers will double every 2 years, making the computer performance better and better day by day, which is a fact we all are witness to. These, together with the recent successes in describing and predicting properties of materials, electronic structure calculation has become increasingly important in the fields of physics and chemistry, and now extended to biology over the past few decades. However, solving just the electronic problem turns out to be a notoriously difficult problem, as it involves many electronic degrees of freedom. The simplest possible and the most obvious approximation to make is the single-electron approximation, in which one replaces the many-electron problem by that of a single electron which moves in the mean field created by the other electrons and the nuclei. Several different formulations of the single-electron approximation are available. Today we will discuss the Hartree approximation, which gives the best possible one-electron wave functions that was published by Hartree in the year 1948. Douglas Hartree was an English mathematician and physicist who derived the Hartree equations for the distribution of electrons in an atom and proposed the self-consistent field method for their solution. As we proceed along the next lectures, we will find this concept of self-consistent field solution will be applied again and again and is in the heart of the modern day electronic structure calculation. With this brief introduction, we now move to the details of the Hartree method and the single-electron approximation. The objectives of this lecture are the following. First, we will introduce the basic electronic Hamiltonian. From there, we will argue the necessity of single-electron approximation. We'll then discuss the matrix elements of the electronic Hamiltonian in the single-electron basis. The electronic Hamiltonian consists of the single particle operator and the two particle operator. This will create the necessary background and foundation to introduce and discuss the Hartree method, where we will discuss the concept of variational method and self-consistent field solution. As we know, the electric, magnetic, and optical properties of materials are controlled by their composition and structure. The structure and the strength of the material, in turn, are determined by the chemical bonding between the atoms. As is shown in the picture, there is this two famous kinds of bonding is shown. In the left panel, what is shown is the covalent bonding, where the electronic cloud is shared between two atoms. And the next one is another famous example, is that of the ionic bonding, where the electron is transferred from one atom to another atom. This forms the two prominent kind of bonding other than the hydrogen bonding, van der Waals bonding, metallic bonding, and others. Thus, the chemistry controls the physical properties, and at the root of all of these are the electron. Understandably, the understanding and calculation of electronic structure that forms an important topic in the area of condensed matter physics, chemistry, as well as the biophysics, which is the topic of our discussion. This is because the electrons at the microscopic level govern the behavior of the materials, as we have mentioned. Good description of many macroscopic properties are obtained in terms of two major approximations. The first one is the Born-Oppenheimer approximation, which has been already discussed. The essence of this approximation is that the nuclei and the electrons, to a good approximation, may be treated separately. This is justified by the fact that the motion of the nuclei, which are much heavier compared to that of the electron, is significantly slower compared to that of the electron. Even after the Born-Oppenheimer approximation, we are left with many-electron problem, which is an impossible task to solve. This calls for further approximation, namely the one-electron approximation, which will form the topic of discussion today. The essence of this one-electron approximation is that each electron behaves as an independent particle moving in the mean field of other electrons plus the field of the nuclei. The basic electronic Hamiltonian that is obtained after the Born-Oppenheimer approximation of decoupling the electronic degrees of freedom from the nuclei consists of three terms as is shown in this slide. The first term is the kinetic energy of the electrons. The second one is the attractive potential, which is generated by the fixate of nuclei. And the last one is the potential that is generated out of electron-electron repulsion. The Hamiltonian thus can be divided into an one particle part, which is shown here as little hi. This is called one particle part because the involved term here depends on the coordinate of a single electron, which is designated as I. The other is the two particle part because the terms involved here, which is given by this little vij, depends on the coordinate of the two electrons, namely I and j. The wave function psi is thus function of position and spin coordinate of n electrons. Since the Hamiltonian does not include any spin-dependent part, the wave function psi can be broken into space and spin parts. Analytical solution of the Schrödinger equation h psi equal to E psi for the space part of the wave function psi is not possible because it depends on too many variables. One may try to solve it numerically by constructing a grid in real space and evaluating the wave function at each and every point. For example, one can choose a different values of the real space coordinate given by x, y, z and evaluate psi numerically at these points. One needs to remember that the wave function psi depends on the 3n coordinates of the n number of electrons. So if there are 50 real space coordinates specified by x, y, z, one needs to find the wave function psi for 50 to the power 3n points. As is clearly understood, this will be an impossible task if the number of electrons n and the real space coordinates x, y, z increases. This calls the necessity for the single electron approximation, which will be discussed in the following. The most obvious and simplest possible approximation, as we will discuss in solving the many-electron problem, is the single electron approximation, where one completely neglects the two-particle term in the Hamiltonian, which is given by the second term in the Hamiltonian, and keeping only the single particle term shown in the first term of the Hamiltonian. Therefore, the Hamiltonian approximated in the single electron form is given by H0, which is the summation of I of this operator shown by little hi. This operator little hi satisfies the Schrödinger equation little h psi equal to epsilon psi. This can be solved as this problem involves only one space coordinate r. One can then write the solution of little hi, where I runs from 1 to n, as psi1 r1, psi1 r2, etc. and etc. The corresponding wave function, taking into account the spin part being given by phi1 x1, phi2 x2, etc., where x involves both space and the spin part of the coordinate. The corresponding eigenvalues are given by epsilon 1, epsilon 2, etc. Now, without violating Pauli's principle, one may choose these single electron wave functions given by phi a1, phi a2, etc. to accommodate the n number of electrons. Since we have the underlying Schrödinger equation of the single electron that is given by little hi phi ai equal to epsilon ai phi ai, one can have little hi product of all the phi's equal to epsilon ai product of all these phi's. Therefore, taking the summation over I on both the side, one can write the H0 times product of the phi's equal to E0 capital phi, where capital phi is the notation introduced to indicate the product wave function, which is the product of all these little phi's. The corresponding eigenvalue is given by this capital E0, which is nothing but the summation of the single electron eigenvalues, that is epsilon A1 plus epsilon A2 plus epsilon AN goes on. Assuming that there is an orthonormality between these single electron wave functions, it is easy to show that the capital phi's also satisfies the orthonormality condition. The eigenvalue equation within the single electron approximation is thus given by the determinantal form which is shown here. In principle, this is an infinite dimensional equation. In practice, one takes finite dimension and checks for the convergence in the result by increasing the dimension. We have this single electron equation, little h psi equal to epsilon psi, where psi depends on the coordinate of one electron. Thus, in the previous example, considering 50 real space coordinates given by xyz, psi needs to be calculated at 50 to the power 3 points. For n number of electrons and eigenvalue equation of dimension given by capital D, the calculation needed are thus capital D times n times 50 to the power 3. This is a huge simplification compared to what we discussed previously, 50 to the power 3n calculation needed for the full many-electron problem. By introducing the single electron approximation, we thus achieve a huge simplification in the problem. It is, however, too crude to neglect the two-particle term completely, as we have done so far. A better approach would be to consider the part of the electron-electron repulsion, which is the two-particle term in the Hamiltonian, in H0, so that the difference between H and H0 is not large. However, we need to remember the part to be included must be function of coordinate of one electron only, so that it can be solved. So the H0, taking into account apart from the electron-electron repulsion, now should look like summation of over I, little hi, plus an additional term, summation over I, a phi. The single electron equation in this case will be given by little h plus f times psi equal to epsilon psi. Of course, one needs to have a prescription how to choose f, which will be discussed later, but this introduction of f involves the concept of mean field. which is shown in the cartoon picture here. That is, as shown in the left panel of this cartoon picture, there are this collection of electrons which are shown with little dots, and from there one isolates one single electron which is encircled, and in the mean field approximation one assumes that one takes this electron out of the system, and the electron now interacts with the mean field which is formed by all other electrons. So instead of having this detailed structure of this n-1 electron, this is replaced by a homogeneous field through which this isolated electron interacts with. We note that the correlated motion of electrons in this approximation is completely neglected. We now proceed to calculate the matrix elements of the Hamiltonian in the single electron basis. As we have already discussed, since the Hamiltonian consists of the two terms, the single particle term and the two particle term, the matrix element also consists of two terms, one involving the single particle operator, another involving the two particle operator. In the following, we'll use the bracket notation as is shown here, because it's more convenient to use the bracket notation in terms of the detailed wave function notation as is shown in the right hand side, and the bracket notation is shown in the left hand side. We have already introduced the capital phi's, which will be labeled as phi A and phi B, which are two product wave function. In case of phi A, they consist of phi A1, A2 until phi AN, and in case of phi B, they consist of phi B1, phi B2 until phi Bn. Let us first consider the single particle operator and consider the situation where this single electron wave function levels for phi A, namely AP, is equal to the levels in phi B given by BP for all P. In other words, now phi A is equal to phi B. In this case, the matrix element is given by AI little h AI. So the summation over I gives us just summation over I AI little h AI. Let us now consider the situation where we have AP equal to BP for all P except K. In that case, the matrix element is 0 until and unless the I, which is the label in the Hamiltonian, is equal to K. And in this case, the matrix element is given by BKHAK. It is easy to prove that the matrix element is equal to 0 if these single particle labels become different for more than one pair. That is, AP is equal to BP for all P's except P not equal to K and L, let's say. In that case, one can prove very easily that the matrix element is equal to 0. The two particle operator and its matrix element can be deduced in a very similar manner. We note for this two particle operator, it connects two coordinates, and it's a symmetric operator because it remains unchanged if you interchange xi and xj. Calculating the matrix element in the same spirit as we have done for the single particle operator, we find that it is given by half summation over ij ai aj v ai aj if AP is equal to BP for all values of P. If AP is equal to BP for all P except K, then the matrix element is given by summation over I, AI, BK, V, AI, AK. Note the factor half is missing here because the label K can be for the A's as well as for the B's. However, since the operator V is a symmetric operator, the contribution of these two terms are exactly identical, and you can sum them up, and which will cancel the factor half, giving rise to the result summation over I, AI, BK, V, AI, AK. If AP is equal to BP for all values of P except K and L, then the matrix element is given by BK, BL, V, AK, AL. With this gained background, we will now discuss the Hartree method. The method was pioneered by Douglas Hartree, who was born in the year 1897 in Cambridge and died in the year 1958. In developing the Hartree theory, Hartree was influenced by the earlier semi-empirical methods of 1920s, which was introduced by Fuse, Lindsay, and himself within the framework of the old quantum theory of Bohr. The energy of a state with principal quantum number n following Bohr's theory is given by E equal to minus 1 over n square. However, it was found that the energy levels of the many-electron atoms obtained from the atomic spectra can only be described by applying a modified formula given by E equal to minus 1 over n plus d square, where d is an empirical parameter arising out of electron-electron repulsion. Hartree aimed in doing away with the empirical parameters and solve the many-electron problem from fundamental physical principles. In other words, in an ab initio way. His proposal became known as Hartree method. The basic assumption of Hartree theory is given by the form of the wave function expressed as a product wave function, as is shown here, where it's a product of all the single electron wave functions in the levels A1, A2, etc. until An. However, this single electron state given by little psi ai in general is underdetermined since the term f in H0 is not specified. The prescription given by Hartree to determine f is the following: use variational method, minimize the energy with respect to the wave function psi. This gives the equation for psi. Compare this equation with the single electron equation given by little hi plus fi times psi equal to epsilon psi. This gives the form of f. Considering the orthonormality of the single particle states given by product of a k equal to 1, which gives product of psi equal to 1, the total energy is given by the following set of equations, which are shown in the bracket notation as well as in the wave function notation. Please note that in the summation in the second term, we have used a kind of hash here. That means I is not equal to j. This will be important as we discuss the next slide. We need to remember the wave function psi is a stationary state of the system. Any variation in wave function should give zero variation in energy. Take the variation in the wave function to be given by delta psi I, for example, together with the constraint of the orthonormality of the wave function as is shown here. The procedure to handle such situation is the introduction of the Lagrange multiplier, let us call it as epsilon ai, and consider the variation as is shown here. Varying the wave function psi ak in this equation, one therefore gets the following equation. Note here in the summation over j, we are still carrying the symbol of this hash, which means the summation over j includes everything except k. Since the above is true for any variation of the wave function little psi, we have the following equation, because by setting the term inside the bracket in the previous slide equal to 0 is given by the first line in this slide. This gives us the form of f, which is shown here in this 3 subsequent equation, just expanding a bit on the form of this psi and phi. We note here that f depends on ai because the summation over j excludes ai. So f therefore is different for different psi's or phi's. Thus, for calculating f, psi's must be known. However, psi's can be calculated only if f is known. So we have a funny situation where psi is both input and output. This leads to a problem which can be solved by imposing self-consistency as is described in the following cartoon figure. We assume some form of this wave function, the single electron wave function, given by phi. From there, we calculate f by using the equation shown in the previous slide. One then solves the Schrödinger equation given by little h plus f times psi equal to epsilon psi to get the form of the psi. From there, adding the spin part, one gets the phi, which is like a phi nu. One then replaces the phi old with this new phi and repeats the step until one reaches a convergence. What one means by convergence is the difference between the phi new in one of the step and the phi old in the previous step. That difference is less than some pre-assigned value. What that pre-assigned value will be depends on the user and how much of accuracy is needed. Finally, the total energy of the system under Hartree approximation is shown in this slide in detail in the bracket notation. Note that the total energy of the system can be obtained from the above by adding the ion-ion repulsion energy to this above equation. Because within the Born-Oppenheimer approximation, in the electronic problem, one neglects the nuclear motion, but still one has to take into account the repulsion between this one nuclei with another. To summarize, a great deal of simplification is obtained by single electron approximation of the many electron problem, which otherwise would have been impossible to solve. The Hartree theory in this respect is the first step forward, which expresses the wave function of the system as product of single electron wave functions. This leads to the self-consistent approach, as the potential contains the information of the wave functions, while the wave functions themselves are the solutions of the problem.